Welcome back. Professor Baldwin here. We've been learning a lot about exponents and logarithms. So today we're going to do some applications and models that use growth and decay, or exponential growth and exponential decay. So they're exponent functions. First, we're going to look at exponential growth, which follows this function, p of t. And with exponential growth, we talk about the doubling time, or how long it takes for a value to double in size. Our first application example says that in 2014, the population was approximately 438,000, and the growth rate was about 3.4% per year. So going back to our equation, what is it that we know? Well, 438,000 is p of 0, or the population at time 0. And then our growth rate, 3.4%, remember those always get written in decimal form. This is our k, or our rate of change. For part A, we need to find the exponential growth function. We are going to take the given function for exponential growth, p subscript 0 e to the power of kt, and we're going to substitute in what we know. P of 0, the population at time 0, was 438,000. And then we have e, our k is 0.034, and it's at a time t. Here we have the exponential growth function for this specific problem. In part B, we want to estimate the population in 2017. 2017 would be a time of 3 years, since that's 3 years since 2014. So we're calculating P of 3, or 438,000 e to the power of 0.034 times 3. Let's plug that into our calculator. So we have 438,000. Then we have e, so second e to the power of 0.034 times our time of 3. And we'll hit enter. So after 3 years, or in 2017, the population is 485,033. So 485,033, I guess it was 34 if we round to the nearest whole person. Part C, when will the population be 500,000? Well, we need to solve 500,000 equals our given equation, and we're trying to solve for t. So first we need to divide both sides by 438,000. So we'd get 500,000 divided by 438,000 equals e to the 0.034 t. Notice that these zeros would simplify out, so we'd have 500 over 438. Since we have e to the power, we're going to take the natural log of both sides, because by taking the natural log of e to a power of something, we get just the exponent. So on the left, we'll have the natural log of 500 over 438 equals just the exponent part of the right, 0.034 t. And then solving for t, we would divide both sides. So t is going to be equal to the natural log of 500 divided by 438 over 0.034. And we're going to go back to our calculator for that. So we need to find the natural log of 500 divided by 438. That's our numerator, divided by 0.034. And we get 3.89. Or that's approximately equal to 4 years. So part C tells us that in about 4 years, the population will get to 500,000. Now part D. Part D, I need to scroll back up so we can see that equation for doubling time. Remember that doubling time is K times T equals the natural log of 2, or you can rewrite it in these other two formats. We want the actual time, so we're going to use the last. That time is equal to the natural log of 2 divided by that rate of change constant we have, which is 0.034. We go back to our trusty calculator, and we're going to find the natural log of 2 divided by 0.034, and we get 20. So doubling time equals 20 years. Let's look at another example. And here we're going to look at an investment. Suppose that $10,000 is invested at an interest rate of 5.4% per year, compounded continuously. Compounded continuously is what tells us to use an exponential growth model. The 10,000 is P of 0, or the initial amount that we start with, and the interest rate is our K. And remember, that needs to be in decimal format. First, we need to find our function. So P of T is equal to the initial amount we start with, 10,000. My pen's not cooperating. Times E to our rate, 0.0054 at time T. Now, part B is asking for two different values, the balance after 1 year and the balance after 10 years. Well, after 1 year, that would be 1 time as 1. So we substitute in a 1 for our T. And we can plug that into our calculator. We'd have 10,000 e to the power of 0.054. Since it's times 1, it's just 0.054. And that amount is $10,554.85. So after 1 year, it goes up to $10,554.85. Okay, how much money do we have in 10 years? Well, we do the same process, except now our T is going to be 10. So 0.054 times 10 for our exponent. And use your calculator. So again, we start with 10,000, and then we have e to the power of 0.054 times 10. After 10 years, we have $17,160.07. So we'll write that, $17,160.07. C wants to know the doubling time. This is really important. This will tell us how long that money needs to be in the account at that interest rate in order to double. So in order for it to become 20,000. We know that it can't be much larger than 10 years, since in 10 years we're already at 17,000. Well, recall that doubling time is equal to the natural log of 2 divided by that rate. And we use our trusty calculator. So natural log of 2 divided by our rate, and we get a doubling time of 12.8 years. So those were two examples of exponential growth. One with a population growing exponentially, and the second where we have an investment that's compounded continuously. Our next example is exponential decay. And notice that the function looks very similar to exponential growth. The only difference is that we have a negative exponent. And look at the half-life is found with the exact same formula as doubling time. Our application example here is that the radioactive element carbon-14 has a half-life of 5,750 years. The percentage of carbon-14 present in the remains of organic matter can be used to determine the age of that organic matter. Archaeologists discovered that the linen wrapping of one of the Dead Sea Scrolls had lost 22.3% of its carbon-14 at the time it was found. And we want to know, how old was the linen wrapping? Well, what is it that we know? We know, first, the half-life is 5,750 years. Well, that means we know this part. So let's start there and figure out our constant K since we know the half-life. So we need to use this second equation because we're trying to find K. So K is equal to the natural log of 2 divided by our half-life time, 5,750. And our calculator tells us the natural log of 2 divided by 5,050 is equal to 1.2 times 10 to the negative 4. Or if we want that in decimal form, that would be 0.00012. Right? We have 4 decimal places from the 1.2 to 0.00012. So from this, we can now set up our equation. So P of t equals P subscript 0 e to the negative 0.00012 times t, right? We substituted in the k, our percent change value. Now we just need to start filling in the rest. We need P of 0. And how do we get P of 0? Well, notice that we're told that we have 22.3% of its carbon left at the time it was found. Oh, sorry, it had lost 22.3% of its carbon. Lost 22.3. So if it lost 22.3%, it has 100 minus 22.3, or it has 77.3% is present. So that means 77.7% of the initial amount is what is left. Well, P of t is how much is left. And we know that 0.777 of the initial amount. This is 77.7% of the initial amount. That's what's left. Is equal to the initial amount, e to our exponent. Now notice that we have P of 0 on both sides. So we can divide both sides by P subscript 0, and they'll simplify out. Notice what we're left with. On the left, we have 0.777 equals e to the negative 0.00012t. Since we have e to a power, if we take the natural log of both sides, that'll leave us with just that exponent on the right. So the left is the natural log of 0.777. On the right, that's equal to 0.00012t. And to solve for t, we'll divide both sides by negative 0.00012. So t is going to be equal to this, the natural log of 0.777 divided by 0.00012. Back to our trusty calculator. We need to find the natural log 0.777 divided by negative, remember to use the negative symbol and not the minus sign, 0.00012, and we get 2,103. So this is telling us that the time for this linen wrapping to get to 77.7% of its initial amount left was 2,103 years. So this is 2,103 years old. I hope you found this video helpful. If you still have a question or you come across a problem that you need help with, leave it in the comments and I'll happily include it in one of my videos.